Let's start. Do you have any questions? Right. So last time we were discussing 4.3 classification of states. Right, of a Markov chain. All right. And so let's review the basic ideas here, or the basic concepts here. So first are the definitions, right? So let's see, these are important details. So first thing, right, is about the connection, or right, the connection between two states. J is accessible from I if P_T ij is positive, right, for some t. So this one also means that exists, right? T equal to 1, right? Such that. So basically, if you can go from I to J using a path, right, of length t with positive probability, then J is accessible from I. And Ij communicates if they're accessible, right, from each other. So that's just a definition. But then, right, we have the idea that basically this relation right here defines an equivalence relation, right? Communication defines an equivalence relation, which means it satisfies, okay, sorry. So here, yeah, I keep forgetting, right? This is starting from 0 because it would allow for state I to communicate with itself, right? So it satisfies identity, symmetry, and then transitivity. Right? And equivalence relation, the reason why we care about equivalence relation is because they break the whole universe, right, which is the state space here, into equivalence class. Okay. So basically, our task, right, is then to analyze or characterize these communicating classes. A typical example for us, right, is the one where we have, I mean, this doesn't have to be the only, right, definition example, but I don't know, right? Something like that. Okay. So here we have three, right, communicating classes. Zero, one, two, three, and then four, right? Now, our task is our next goal, right, is to classify these classes, right? And if you remember, the point is that these two classes are called recurrent, and this is called transient, right? Which means that basically, right, if you're in the class, you will stay in the class, while if you're in a transient class, then you will eventually, right, escape the class into somewhere else, into another class. So that's what we're gonna do next to define recurrent and transient, right? So so I guess we have to define f sub I is the probability that you ever, right, return to state I. And here you actually need to take at least one step starting at I, right? So starting at a state, will you ever return to that state? And if you do, if you're guaranteed, right, to return to the state, then this makes, sorry, let me say by definition, right, state I is recurrent if you're guaranteed to return to that state, starting there. And state I is transient if, sorry, guaranteed, right? If that's not so, right? And so here, fi less than 1 means there is a chance, right, that you will notice, right, the negation of this, right, the complement of this. Right, is probability that xt is not equal to I for all t. Right, and so that's what it means to be sort of escaping, right, from the state. Well, we kind of exchange, right, the words state and class here, because we'll say, right, very soon that recurrence and transients are actually class properties rather than state property, right? But so far, right, these are definitions. Whether you're guaranteed to return or there's some chance that you will never return, right? Because if fi is less than 1, then 1 minus fi is positive, right? So, okay. So again, right, intuitively, we see that under this definition, then state 4 or class 4 is transient, right? And these two classes are recurrent. But I guess how to prove it, or in general, right? In general, how do we show that a class is transient or recurrent? You know, it's not all that easy, because when you have, like, let's say 100 by 100, right? Or even more. I think this is actually connected to graph theory, where I forgot what in graph theory what the term is, but they also have the idea that if different nodes, right, a collection of nodes are connected among each other, then they form a class, right? And one problem in graph theory is how to classify, how to quickly find this, again, communicating classes, right? And it's not easy because, you know, one way you can do is you just start from a state and just keep following, right? Another state until maybe you return to that state. But you may or may not return, right? Because there's so many paths to follow. So basically, the point is you could try to explore all possible paths leading from a state and to see if you ever return back to that state. Well, it's doable if you have a small number of states. But if your number of states like 100 by 100 or like, let's say 1,000 by 1,000, right? Then it's pretty challenging, right? To just do it by searching all the paths, for example. So to be able to say quickly whether a state is transient or recurrent without, of course, resorting to the path idea, right, is some kind of like practical question that we need to be able to solve or be able to say something about. So let's see here. So then, right, so let's write down, right, how to check if I is recurrent or transient. Let me say, without, let's say, going through all the paths starting from I, right? And so here we have the idea of what's called a number of visits, right? Or let's say number of revisits. Let's call this n sub I, right? So basically n sub I, well, how to say this? We need to define one more variable, right? We need to define I sub n to be 1 if x sub n is equal to 1. So x sub n is equal to I and 0 otherwise. So this is the indicator function that the chain visits state I, right, at time n. So the number of visits to state I starting at I will be the sum, right, of I sub n and from 0 to infinity condition on x0 equals to I. That's n sub I. Okay. So you're defining, right, as we analyzed last time, a geometric kind of random variable here. Like we define a geometric random variable here because you allow for the initial value to be 1. Because you sum, right, from n equal to 0. So you're guaranteed, right, to visit the state at least once. But each time that you return, right, that's, well, in the language of geometric random variable, that's a failure, right? That's a failure to escape. Okay. But each time you return, well, you will return with probability fi, right? Or you will escape the probability 1 minus f sub I. So starting at I, if you ever return, okay, if you ever have a chance, right, to escape, intuitively you will after, right, so many trials. So basically, yeah, here's the thing. I guess, hold on. And also there's something called, right, the strong Markov property. Which states that, which is like Markov property, but it's applicable to random times. Basically, it says that once, so okay. Let me just state it. So Markov property also applies to stopping time. That's the technical detail. I cannot just say random time. The technical word is stopping time. But as far as we are concerned in this context, all it means is that once the state, or sorry, the chain returns to state I, you can basically forget, right? You can forget whatever has happened before. Meaning that once you know that it has returned to state I, however many steps it takes to do so, then basically from there, it's just going to be transitioning from state I to another state in so many steps, right? So basically, for example, as far as the question of revisiting is concerned, right? You see, I guess the technical thing here is that you have to have a definite time to say starting at time 0, I'm at I. But the question of return, right? It's never really about fixed time because the Markov chain is random, right? So the first time to revisit is going to be a random time. You cannot say, well, at time 10, I will revisit state 3, right? You cannot say that. Sometimes at state 10, I revisit state 3. Sometimes at time 15, who knows, right? I revisit state 3. But strong Markov property says that it doesn't matter, right? When I return to state 3. But the moment I return, I will move from state 3 to other states as if I started right at state 3 at time 0. That's sort of what it says here. But and if you carefully think about it, strong Markov property is a subtle thing that needs to be proven, right? Rigorously, let's say. We're not going to do that here, okay? We're going to kind of accept that as some sort of like intuitive thing that is true. But again, let me emphasize that it's not, it requires some proof, right? But it's rather technical, so we're not going to do it. But anyway, so accepting the strong Markov property, then what we're having here, right, is the idea that starting, right, at state I, that's one visit, right? You get the first visit for free. And then, right, at each time you look with 1 minus fi probability of escaping. That's like your success, right? If you're not success, then you will return back to state I. Okay. And then from there, using the strong Markov property, you will again look for the probability of escaping. And then if you're not successful, you will return, so on and so forth, right? And you can see that, of course, if you have no chance of escaping, meaning if Fi equals to 1, then you will keep revisiting state I infinitely many times, right? Because you have no chance of success, no chance of escaping, right? Fi equals to 1. And so in that sense, if I is recurrent, it's pretty obvious that probability Ni equals to infinitely equals to 1. Because, right, it's a conditional probability. I mean, it's conditioning on the previous step, but each of these step is 1, right? Basically, you have a guarantee of returning, and so from state I, so it's always once when you multiply everything together here. On the other hand, if I is, so of course, if something has probability equals to infinite equals to 1, then that means expectation of that guy is also infinite. Notice, right, the reverse doesn't have to hold. Meaning that, of course, right, if a random variable has infinite expectation, it has to have certain kind of distribution, but it doesn't have to even take on infinite value, okay? With any kind of positive probability for the expectation to be infinite. And we'll look at that, I think, in some example. And I here is transient. Then what? Then Ni will have, as we explained, geometric random variable with 1 minus Fi, okay? Probability of success. Therefore, expectation of Ni is 1 over 1 minus Fi, and let us say it's finite, because 1 minus Fi is not 0, right? It's positive. Okay. And so, well, on the other hand, right, using the definition of Ni, we see that expectation of Ni is expectation of the sum. Right? And we can pass the expectation inside the sum. Remember, right? In is just the indicator function that xn equals to I. Therefore, it's really just probability, right? And that's p to the nii. And so, okay. So the significance here, right, of course, is not that we can raise the matrix P to any power easily. That remains to be seen. But at least from the point of view of not going through the paths, we have succeeded. Because you see, right, again, if you just straightforwardly following the definition of Fi, and you really have to start from a state and check through all possibilities to see if you ever return to that state, which you can take my word for it, it's not a fun thing to do when you have like so many states. By analyzing the number of revisits, then the question boils down to whether you revisit state I in n steps and just sum up all those possibilities. Okay, so probably it's intuitive that the two are connected, right? The probability of ever revisiting somehow is connected to the probability of revisiting, right, after n steps. But you can also try to check, right? And of course, do not make this mistake, right? This is clearly not true, right? What's the reason? Well, the first obvious reason is that this guy is always bigger than equal to 1. Why? Because you have this time 0 here, right? Built in. So this guy is always greater than equal to 1. And of course, Fi is a probability, so it's always less than equal to 1, right? So they can't ever be the same. But even besides the technicality that we count times 0, right, into our Ni, the point is that P to Nii, these are probabilities that are not mutually exclusive. Okay. Basically, what it means is if you visit state I in 10 steps, so the event that you visit state I in 10 steps, and the event that you visit state I in 8 steps, right? So these two events. Well, these are not mutually exclusive, right? Because if you're this could have non-empty intersection. Does it make sense? Because depends on how the chain is structured, but basically you could be at state I at time 8 and then also be at state I at time 10. So when you sum this up, you have overlapping, right, probabilities. I'm referring, of course, to the idea of inclusion-exclusion principle, right? Fi is the union, right, if you will. Fi is the probability of the union over all possible t's, but starting at 1. Like that. It's the union of these events, right? Because that's what we say when we say equals to I for some t starting at I. Okay? And so that's why it's not the sum, even if you start at 1 here. Because if you want to reconnect this, and this is the inclusion-exclusion formula you have to follow. So this is why this is not something that obvious, because somehow, right? Well, so I guess I keep talking about this without writing down the punchline, right? The punchline is already here, which says that I is recurrent if the sum P to Nii is infinite and I is transient if the sum, right, is finite and is equal to this. Okay. So again, the point is that this sum is way larger than Fi in general. But this sum is, in terms of the path, it's not complicated because you always follow the path of n steps back to I. And in terms of the transition matrix, it's just raising the transition matrix to n power. Again, practically, this may not be an easy thing to do, but conceptually, right, it doesn't require us to list paths, all possible paths, right, returning from I to I. Anyway, and so here, Fi is indirectly, let's say, figure out from the sum, if somehow we can get our hands on this sum, right? So that's sort of the answer, right? One possible answer to how to check if a state is recurrent or transient without going through all the paths. The answer is by analyzing the number of revisits. Okay, starting from state. Okay, any question? This is just reviewing, right, of the old materials. But okay. So now the next point is that recurrence and transience are communicating classes. Properties. Okay. The precise statement is that if I is recurrent, I and J communicates, then J is recurrent. On the other hand, if I is transient, and again they do I and J communicates, then J must be also transient. Okay. And so this is why, right? These are class properties because they get propagated, right, via the communication equivalence relation. So if you remember, right, the proof of this relies on this sum. So basically, right, another way to state this is the sum of P2. If I and J communicates, then the sum P to NII is infinite if only if the sum is infinite, like that. And of course, right, because it's if only if, so if it's finite here, it's finite there. Okay. And so this property, right, which is very important for our analysis of Markov chain, relies on this way of characterizing, right, a recurrent or transient state. Any question? All right. Let's see what else we have. I think with that, we are done with the materials of 4.3. We're just going to do the problems, right, to demonstrate these ideas, and then move on to 4.4. Yeah, we're done with the materials, right? So, oh, sorry, just one more technical thing, right, which you've seen before, but we mentioned this, but we say that a Markov chain is irreducible if it only has one communicating class. Now, I guess then, right, an interesting question is, so basically this is the definition. A Markov chain is irreducible if it has only one communicating class. The obvious question to ask here is what? The obvious question to ask is, well, is that class recurrent or transient, right? The definition doesn't say that, doesn't say which one. Can we add that detail or we can't? Do we know if, right? Let's just say this. A chain is irreducible, then it must also be recurrent. Or in other words, can we have an irreducible but transient Markov chain? What does that mean? Right? Because you think about, basically, transient has the sense of escaping, right? But if you only have one class, what are you escaping into? So is it true? Is it true that if a chain is irreducible, then it must be recurrent? No other choice. So the answer is no, that's not true, okay? But you need something a little bit more sophisticated. So let us write down the proposition first. So answer, right? Not necessarily. Meaning you can have a Markov chain with one class, so it's irreducible, but it will be transient. It can be transient. So the following proposition: a irreducible or an irreducible finite Markov chain is recurrent. So this proposition actually tells us what's going on with this question. So by itself, irreducibility is not enough, okay? But we need an extra condition called finite. So finite here refers to the number of states, right? If you have a finite number of states, then irreducibility is enough is sufficient to guarantee recurrence, which implies that if you are looking for an irreducible transient Markov chain, then you have to look to infinite, right? The infinite case, meaning that you have to look at Markov chain with an infinite number of states. And a obvious example will be random walk, okay? But let's see how we can prove this first. Prove that an irreducible finite Markov chain is recurrent. How do we prove this? So here, right, what do we need to prove? So first, by irreducibility, you have only one class, right? So because recurrence or transient is a class property, it's enough for us to prove, let's say, state 0, right? One state is recurrent, whichever state that is, let's call state 0, right? Now, so let's focus on one state, let's say state 0. Okay. Now, what technique will we use to prove that state 0 will be recurrent in a finite irreducible Markov chain? Well, as we mentioned, right, f of 0, right, the probability that you will return to 0 starting at 0 is a hard thing to compute. So let's look at the number of visits to state 0 starting at 0, okay? And we need to use, or we need to utilize, right, the finite property somehow. And let's say this, right? Let's suppose by contradiction, right, that the state 0 is transient. That means that the number of visits, right, must always be finite. All right, the number of visits must always be finite, because that's the point, right, of a transient state, that expectation, right, of the number of visits will be this sum, which is finite if it's transient. Okay. And well, what's, let's say, wrong with this picture if we have a finite Markov chain and irreducible? I guess finite's enough, right? Well, maybe we need irreducibility. What you think about, right? basically, if you start at 0, right? Then if you want to avoid revisiting 0, right? If you want to avoid revisiting 0, then you need to basically return, sorry. Let me see how I can phrase this a little bit more clearly. Sorry, give me a moment. What do I want to say here? Sorry, I think I know what I'm trying to say. It's not that. So, okay, so suppose a state 0 is transient. That means, right, n0 is finite, but that's not enough. Now I will use the fact, right, that transience is a class property. So we only have one class because it's irreducible, right? Since the Markov chain is irreducible, this means all states is transient, right? Which means the number of revisiting is finite. For any I. Okay. So basically, if you look at all the states together, the number of revisiting for each of the states will be finite. But what's the problem with this? The problem with this is as followed, right? If you start from time 0 and time 1, time 2, etc., then basically, right, let's say at time 0, so this is time. Let's say you are at state 0, right? And then from 0, you move to state 2 or whatever, right? And then you move to state 1 and then state 4, etc. Then basically, eventually, you may or may not return to state 0, but you will, let's say from state 2, return back to state 2, right? The point is, because you only have finitely many states, then if you sum up, so my point is this, if you sum up all, so R here, right, is the number of states in the Markov chain. Okay. If you sum up all the number of revisits, so, sorry, I from 0, let's say, right, across all the states of the Markov chain, then what does this give you? This should give you is the amount of time passed. Does that make sense? Because if you basically, whenever you add a state, the number of visits counts as 1. And then if you return there again, it counts as 2, 3, etc., right? So basically, if you look at the number of visits to all the states in the Markov chain, you sum that all together, that's the amount of time it's passed. But of course, right, what kind of horizon are we looking at here? Infinite. So actually infinite. Are we clear on this? And yet, right, what's the point? The point is that here, all the number of revisits is finite by our assumption, right? Suppose that one state is transient, and that means all states is transient. All states are transient. So this is supposed to be finite by our contradicting assumption, which really means that the assumption is false, which means that, right, it must be recurrent. All right. Any question about this proof? So, right, it just plays on the idea of it's actually, in a way, it's like the pigeonhole principle, right? You look at all these times that have passed so far and wonder that at all these times where the Markov chain is, it must be at some state. But if it is at some state, then the number of visits to that state will register, right, that visit. So if you sum up all those number of visits, you should get all the time possible, which is infinite. But on the other hand, is you assume that you only have finite number of states, that's finite. Okay, or long story short, if you don't even make this assumption, right, then this identity is always true. Okay. But if you have a finite sum and it's equal to infinite, so let's say the short idea is this. The sum is always infinite. This is an identity. But since the sum is finite, then that means there exists, just from calculus point of view, some state such that this is infinite. But then by communication or by irreducibility, all states are recurrent. Right? This means I is recurrent. Right? So that's a short proof. Any question? All right. So I guess that's sort of the application of the irreducible concept, right? If you have an irreducible Markov chain and it's finite, you know for sure it must be recurrent in some way because it has no place to escape to. Okay. So what's the follow-up question to this? Well, the follow-up question is then, well, give me an example of an irreducible infinite Markov chain that is transient, right? So that's an obvious follow-up question, right? And the answer is as follows. It's actually, let's call it a theorem, right? So this is about the one-dimensional random walk. So RW means random walk. is recurrent if and only if P equals to, you know what? Let's not even go there. If P equals 1/2, and it's transient if P is not equal to 1. Okay. And what's a 1D random walk? I think this is well known enough to a lot of folks, right? So basically, the sort of the convention is you start at 0. You move to the right with probability P, and at each step, you move to the right with probability P, and you move to the left with probability 1 minus P. Okay, so that's a one-dimensional random walk. So now, why do we say that it's infinite? The reason is you could, make a one-dimensional random walk finite, let's say by stating what must happen at the boundary. So you could, for example, limit a random walk, one-dimensional random walk to state 0 to state n by, I don't know, maybe making the state absorbing and preserving the probabilities of left, right at any other states. That's fine, right? What that means is eventually you will be either absorbed at state n or absorbed at state 0. That's the gambler's ruin problem, right? The question there, you start at some states, what's the probability that you'll be absorbed at state n rather at state 0? Okay, we'll look at that problem if we have time. But that's not the question. I mean, so that's one question. That's a question. But I'm just pointing out that you can make this finite, right? Also by, let's say, reflection, meaning that if you can state that if you reach the boundary, then you either stay there or you go back, so you don't move forward anymore. You can have a reflection, right? Probability, whatever. So that's a finite random walk, right? Finite 1D random walk. The infinite random walk has no such restriction. At all points, you move right with probability P, move left with probability 1 minus P. Okay. Now, so the obvious claim, so the claim is that if P is 1/2, right? 1/2 means it's a symmetric random walk. Then you will be recurrent, meaning that you will revisit a state infinitely often. But if you are not equal to 1/2, then you will visit the states only finitely many times. And there you can see why this makes sense. So the escape concept is not about escaping into something, or if you will, it's like escaping into infinity, right? Because in order to not revisit 0, all you have to do is, let's say, keep going to the right. Okay, then you will not revisit 0. Now notice with finite Markov chain, you can't do so, because at some point you are forced to return intuitively, right? That's what happens. But with an infinite Markov chain, you have room to keep going without coming back. And that's sort of like the idea, okay? Again, of course, that's just intuition. We have to prove all of this rigorously, okay? Because that's the whole point of stating all these definitions. Be very careful of taking any argument here intuitively, because that's the sort of like the trap, right? That you think that the statements are so intuitively true that you don't even investigate how to prove. how to prove it rigorously, because everything has to fall back on definition, right? Everything has to fall back onto definition. If you don't have definition to back you up as a calculation, your argument is actually either false or not rigorous. All right. Any question before we start sort of looking at this theorem? So this is a very well-known problem. So there's many ways to approach this, okay? But let's take on this question via a nice tool, right, from your homework, right? This is your question number 17, right? So quiz 2, is it quiz 2? Yeah. So this is question number 17, right, in your homework. Use the law of large number to prove that an infinite 1D random walk is transient if P is not equal to 1/2. All right. So I guess the first question is what is law of large number and what's the role here? Why is law of large number relevant in this one-dimensional random walk? Why is the law of large number relevant in the one-dimensional random walk? First of all, what's law of large number to begin with? It says that if you have a sequence of ID random variables, right? And they have the same mean, and you really need to have finite variance. So variance sigma square, right? But sigma square won't show up in the result. Then the sample average, right? This is what statistics relies on. Will converge to mu, right? As n goes infinity. Okay. If you take the sample average of ID random variables, you will reach the true average or the population, right? Mean, if you will. So what does this have to do with our random walk? Well, the answer is that the 1D random walk actually is a random sum, right? How so? Well, because a random walk, right? Look at the position, right? So let xt be the position, right, of the random walk at time t. Then the position, I mean, it will just be the sum of the steps. Like that. Should I call it I think it should be 1, right? Not 0. So here, right, by doing this, technically speaking, you should add something like this, where this is the initial starting point of the random walk. If I don't add anything, then the random walk is assumed to start at 0, right? It doesn't really matter. But so here, yi will be 1 with probability p, and -1 with probability 1 minus p, right? So yi here are the steps, right? So that's why it starts from 1, right? It's step 1, step 2, step 3, up to step t, right? That will give you position. Okay. And so the random walk is particularly suited to work with any theory that deals with random sum, right? Sum of ID random variables, which include law of large number and central limit theorem. So how do we utilize this to analyze that? Well, the answer is, let's look at the average, right? So you can call this the average position, if you will. But if you divide, right, which is exactly what this is, and you take a limit as time goes to infinity, you should get what the expectation of the individual term of the sum, which is, right, the average step size. But what's the average step size? Is p plus p minus 1. All right. And what's the kicker? The kicker is that if p is equal to 1/2, p is not equal to 1/2. This is not 0. Okay. And that's all we need, right? Because you see, also the statement here, right? Notice whatever you write down a statement in probabilities, you have to kind of qualify it as it really is a probabilistic statement. So here it really means that the probability that the sum over n conversion to mu is equal to 1. All right. With probability 1, this sum always converges to mu. So here, basically it says, right, with probability 1, the average position of the random walk, if we are called this that, will be 2p minus 1, which is non-zero. If p is not equal to 1/2. All right. Well, but if you turn this around, right, then this says that probability at t is equal to t, right, times 2p minus 1, right? You know, again, this is a weird statement to make, but let's say approximately is fine, right? Because limit is approximation. You can make this more rigorous with epsilon delta, blah, blah, blah. Let's not even go there, right? It's 1. What I only need is the following. Notice t is going to infinity, right? And this is a non-zero number. So infinity times something non-zero will be infinity. Plus minus infinity, doesn't matter. Right? And that's all I need, because this says that the probability that the position of the random walk at time t will be either infinite or minus infinity is 1 as t goes to infinity, right? Therefore, it can never be recurrent. Why? Because if it's recurrent, that means it must revisit, right, any state infinitely many times. Do you understand? If it's recurrent, then so let's say if it's recurrent, then it must revisit state zero infinitely many times. That means that even as time goes to infinity, you should see that the state itself takes on value zero infinitely often. So those of you who's taken real analysis, this means that if you look at the sequence of states of the Markov chain, you should see a subsequence of zeros, a subsequence of ones. Of course, the gap, right, is random. You have to wait a long time before you see zero, but right, subsequence doesn't care about that. But you have to see a subsequence of zeros. Now, again, invoking real analysis, because that's, what we're doing here somewhat, then what we're seeing here is a sequence of that either tending to be very large in the infinite sense or very small in the sense of minus infinity. So you can never have a subsequence of zeros, let's say. That means it's not recurrent. Any question? All right. So notice, right? So what we have proved? We have proved that if P is not equal to 1/2, then the random walk is transient. Does that imply that if P is equal to 1/2, then this is recurrent? Well, the answer is no. In the sense that we didn't, that's why I didn't write if only if, right? If you have if only if, and if we proved if only if, then yes, you can do the contrapositive, right? But here we don't have the contrapositive, right? So if P equals 1/2 is transient, I guess the contrapositive of that is if it's recurrent, then it's 1/2. But we want to prove if 1/2, then recurrent. Okay. So we don't have that statement. So that's the next one, right? So I will skip the word infinite, right? We understand that that's what we're doing here. How do we do this? Well, better yet, right? Try to think what tools we use to prove it. So the first thing, right, is that, again, very common thing, right, which is obvious here, is we just need to analyze one state. Because, oh, you know what? Sorry, I took something for granted. Maybe before this, right? Let's do quiz 4. I took one thing for granted, and I didn't even say it right in the previous problem, which is what? Prove the 1D random walk is irreducible. Well, because, right, who is to say that this is obvious? Who is to say that there's only one communicating class in a 1D random walk? I think it's clear, or at least it's intuitively clear, but also, as I said, right, we cannot use the obvious argument or the intuitive argument here. We have to prove everything rigorously according to definition. So how do we know that the random walk is irreducible? Well, what does it mean? It means that you have to prove for all ij, right? I goes to j, and I think that's enough. Because, right, this is for all ij. So if you switch the role, right, it's also j goes to I. So you don't have to do both, right? For any state, you can go from one state to another. So proof is pretty simple, right? Because if I is less than j, then p to the j minus I, right? You just basically you take so many steps to the right, right? So that must be bigger than p to the j minus I. And if j is less than I, then p to the, so you just go to the left, right? So I minus j here. So you know what? Let's use absolute value, right? Ij is just bigger than 1 minus p. Are we clear on this? So basically, it's pretty simple. To connect a state to another state, you can either walk all the way to the right or walk all the way to the left. But the reason is, right, you always have the probability to walk right and walk left. That's why, right, there's only one class. Okay. And so now let's go back to this. Here, right, we want to prove that the random walk is recurrent, and because the chain is irreducible, a basic thing to do here is just to prove one state is recurrent or transient. All right. And that's enough. Now, how many tools can we use to prove state zero recurrent? Well, if you follow, right, the discussion so far, you would say, I hope, right, that the only tool or the useful tool is to consider, right, the number of visits back to state zero, right, which is also just sum of the transition matrix like this, and you want to show somehow that it's infinite. The second way is to look at F0, which is a probability that you return to 0 starting at 0. And you want to show that somehow it's equal to 1. Now I've been, let's say, actively discourage you from using this tool. And well, let's say that I didn't quite actively discourage you. It's just that I try to point out, let's say, the challenge when you use this formulation, because you have to somehow look at the return path, right? Starting at a state. Okay, and it could be complicated. But here, approach B and of course approach A are both viable. And in particular, right, let's talk about approach B. It's viable because the 1D random walk has a pretty, let's say, simple path structure, right? How would you return to 0 starting at 0? Well, you either go right, and then at some point you have to go left, or you go left, and at some point you have to go right. Now, having said that, it's still not easy, because what if you just, keep cycle back and forth, right, between so many states, you know what I mean? So you can go here, and then you cycle back and forth before you decide to go back. But I think, right, there's a question number 15, that deals with this nature of cycle, right, which we won't talk about because we have so many things to discuss. But if you look at number 15 real quick, you know what? Sorry, it's not really applicable here point to point, but I'll state this, and I'll show you why I say these are kind of connected. So number 15 says that prove that if the number of states in a Markov chain is M, and if state J can be reached from state I, it's just a way to say I goes to J, right? Then it can be reached in M steps or less. Okay. So what is this question in of itself? Well, it says that, right, if you go from I to J, and you only have M steps to go through. And if you do know that you can go from I to J, then clearly somehow you don't need more than M steps. Why? Because, what can you do, right? You can just keep trying to avoid J until you have to hit J. But of course, the tricky thing about this question, you can return back to I, right? But so somehow you have to remove the cycle, right? You have to remove the cycle back to I to make sure that you can do it in M steps or less, right? That's the thing. So that's why, right? I say number 15 is connected to this somehow a little bit, because if you recycle back and forth, right, between two steps here before you return to 0, you can in some way remove those cycles and still talk about a positive path back, right? Okay. Anyway, my point being is here, F0, as you will see, the analysis of F0 is actually, let's say, not too bad for the one-dimensional random walk. So we can show both approaches rather than just one approach. Okay, any question before we continue? All right, so I guess we have half an hour. So the goal is to prove B first and then A. All right, and if we have time, we'll do something else today. But the goal is just to prove B and then prove A. So how can we do B? So B here, right, or the analysis of F0 will be something quite common, right? That what we've been doing so far, but basically it's just analysis of the first step. All right. Meaning that, well, you want F0, right? F0 is what? Well, sorry, how to go to 0 from 0? Well, you can first step, go to step 1, and then from step 1, go back to step 0. Also, state 1, go back to state 0. Or you can go to state -1, and from -1, go back to 0. So here we kind of introduce a new terminology, but it should not be that hard, right? Fij is a probability that you ever return to state J starting at state I. Are we clear on this? So this is like, this is the first step analysis, right? So first step conditioning. Conditioning on the first step. Okay, so far. So to return to 0, which is like F00, right? You either move to step 1, state 1, and then return to state 0, or move to state -1 and return to state 0. Okay? Now let's analyze F10. Well, what do we know as state 1? Well, again, first step conditioning shows us what? You either take a step left with probably 1/2, and then you're there, right? So this is 1/2 times 1. 1 here is not one step. 1 here is guaranteed to be at 0 because you already, right? If you return to 0, you're at 0. Or if you move to the right, then it's F20. Okay. And the same thing that goes with F -10, but we'll talk about that later. Any questions so far? You know what? Hold on. Let me see if I want to do this in general with P1 minus P. Because this proof, right, I think can also work with transient too. So the proof, right? So I guess notice, maybe let me point out one thing. The proof using law of large number is actually a very quick proof. But this technique can only show you that the Markov chain transient. It cannot be used to prove that the Markov chain is recurrent. Why so? Because if P is equal to 1/2, then all you get is this number is 0. All you get is the average position is 0. Well, the average position can be 0 in many, many ways. There are many ways that the average can be 0. it doesn't mean, right, that it will revisit any state infinitely often, at least not yet, not directly. Okay. So we need something else. So that's why a large number cannot be used to prove something is recurrent. The Markov chain is recurrent when p equals 1/2. On the other hand, this technique can prove both recurrent and transient. So in that sense, let me switch this to p and 1 minus p, right? Before I specialize to p equals 1. All right. Like that. Okay. So, and then of course, f minus 1, 0, right, is the opposite story. So now, I guess the story seems desperate because, okay, so what? Now you analyze f2, 0, right? The answer is no. Because if you analyze f2, 0, then you will say, well, you can move one step to the right, then one step back, blah, 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 right? It will never end. What I mean is like, first step conditioning seems to keep pushing you to the right and to the left. But the key idea here, key observation in all of these businesses is follow. f2, 0 will be f1, 0 squared. Sorry, okay, so let me say this. That's a bit of a jump. It's f2, 1 times f1, 0. And this is going to be f1, 0 squared. Of course, implying, right, that f2, 1 is equal to f1, 0. Okay, that's a key observation. Now, why is this true? Well, so first of all, right, this should be easy to understand. The reason, right, is that because the random walk is, I don't know, what do you call it, homogeneous, right? To go from 2 to 1 for a random walk, if you, the possibility of ever going to 1 from starting at 2 is exactly the same, right? You just do a translation as a probability of ever returning from 0 starting at 1, right? Because, I don't know, the random walk looks exactly the same. Just one step left. Okay, so far. So I guess here though, right, it's more like of a question. But here what we are effectively using is a strong Markov property. Where we're saying, right, that to go from 2 to 0 to ever return to 0 starting at 2, you must start from 2 and you must cross 1 first. And then from 1, you must start from there and go back to 0. Any question about this? All right. So, but what does this give us? What it gives us is a quadratic equation for f1, 0. All right. And then you can argue what happens when p is bigger than 1/2, p is less 1/2, etc. So let's see here. Do I want to do this still in the abstract? So here, let's see, do I want to pull out a quadratic formula here? Is the question. Yeah, why not, right? If somehow it looks a little bit harder to show it now, you know what? Let me just specialize p is 1/2 first to show you what happens. If p is equal to 1/2, right? Then what? Then you have 1/2 f0 squared minus f10 plus 1/2, right, equals to 0, right? Which, if you multiply through by 2, it says f0 squared minus 2 sorry, f10, f10. Well, guess what one f10 is in this case? Right? And you see, the moment you see this, you know what's going on. It shows that you are guaranteed to return to 0 starting from 1 if the random walk is symmetric. But then, right, you also by symmetry guarantee to return. So therefore, and maybe let me stop here, right? You can try to look at the quadratic and see what happens when p is not equal to 1/2. It'll result in one of them being not equal to 1. That's why you can escape if p is not equal to 1/2. But I think maybe this is our goal, so let's not even go further. But any question about this? All right. So that's approach B, right? Let's look at approach A. Approach A will look at this sum, right? So and similarly, right, we actually have two results. So I kind of skip, right, the p not equal to 1/2 there for you in the analysis of a quadratic, right? Is this quadratic? But you know, you can look at that. But anyway, right here we also have two results. So the question is, how do we analyze this sum? Or maybe this is quiz 5 for you. Write down p to n 0, 0. And let's, not specialize yet, right? Let's say in terms of p, just generic p. So what's the answer? The answer is right. When can you return from 0 to 0 in n steps? The answer is you can't if n is odd, right? On the other hand, if n is even, then what? If n is even, 2k, then basically, intuitively, out of 2k steps, you take k steps to the right and k steps to the left. And so out of 2k steps, you choose k steps that walk to one direction and the remaining walk in the other direction. Like that. Okay. And so summing over all n values is the same as summing over all k values, right? So finite not equal to 0. Why? So here, right, we need to use a bit of something called the Stirling's approximation. It's I don't know, I'm not sure it's a calculus result or a combinatoric result, but we want to use the approximation for the factorial because we need to somehow, right, see what this is when k is large. It says that n factorial is approximately n to the n plus 1/2. Hold on. Yeah. E to minus n square root of 2 pi as n goes infinity. Okay. So if you prefer, is k factorial. So what does that mean? Here we have what? 2k factorial. Right, divided by k factorial squared. So by Stirling approximation, right, that's approximately 2k raised to 2k plus a half e to minus 2k, right? Forget this because it's constant. Divided by so k plus 1/2 e to minus k squared. Okay, so far? Well, what does this reduce to? Notice the 2 here distributes in, right? So you got something like e to minus 2k would cancel with this. You got k to the 2k plus 1, right? So let's see here. You got 2 to 2k plus 1/2, right? Times k to 2k plus 1/2 divided by k to 2k plus 1. Agree? Which will come down to 2 to 2k. This half doesn't do much, but let's just keep it there too. So it's something like 4 to the k, and then 2 to 1/2 is square root of 2, right? And then here, k to 2k cancel. You have a square root of k at the bottom. So that's 2k choose k, approximately when k is large. Okay. So again, the constant won't matter, but notice that a sum will converge or diverge only if the tail ends, when k is large, converge or diverge. Meaning that you can reduce this to k equals to 1,000,000 or so. Because, right, the first 1,000,000 terms doesn't matter in terms of conversions or diversions. So what that means is we can just plug in the Stirling approximation here, because this won't be true for a large k, but we can be free, right, to use that context because the convergence doesn't rely on k being small. And so you have 4 to the k over square root of k times p to the k times 1 minus p to the k, right? And we see what's going on here. This is the sum, right? And if you prefer 1,000,000 or so, doesn't matter, right? I mean, I just use the word, 1,000,000 here is like a symbol to say that Stirling approximation starts to be correct at that point. But you see what's going on here, because if p is equal to 1/2, then p to the k, 1 minus p to the k exactly is 1 over 4 to the k, right? And this sum will exactly be the sum of 1 over root k, which will be infinite by p series, right? P is half. Okay, so far. On the other hand, if p is not a half, then p times 1 minus p actually will be less than a quarter. Okay. And therefore, the whole thing where you have 4 p1 minus p like this raised to the whole k power will be less than, let's say, will be r raised to k, where r is less than 1. So what do we have here? We'll have something like a geometric sum. But, of course, being tempered by something like square root of k doesn't really matter, because it will be finite by, I don't know, take your favorite root ratio test here. But yeah, any root test or ratio test will tell you that this sum is finite. All right, any question? Okay, so what else do I want to do today in the last 10 minutes? So maybe the last question I want to do is question number 16. This is quiz 6. It says this, and even if, we just state the statement, it's going to be useful. Suppose I is recurrent, okay, and I does not communicate with J. Then Pij is equal to 0. So this is kind of useful because it tells you a categorization of recurrent transient, right? So basically, if you have a recurrent class, right, it sort of tells you that if you have a state that is not part of the class, then you cannot go from I to J. Okay, so the text will say itself, right? Recurrent class is closed. It's a universe in and of itself. It doesn't leak out, right? Or in other words, once you enter a recurrent class, you will not go out of it because there's no path out at all. Anything that's connected to a recurrent class will belong to it. How do we prove this? Well, a way to prove this is actually prove the opposite, right? Sorry, to prove the contrapositive. So we keep the recurrent as the working hypothesis. We won't negate that. But we want to show what? If you can go from I to J, if I is recurrent, what does that mean? That means you must be able to go from J to I, which of course means IJ communicates. So therefore, right, it will be contrapositive. Okay, so far? Right, so that's actually will be a proof here, right? If you have a recurrent state and you can go to another state, you can be very sure that you have to go back to I somehow, which makes it into a class. Right, how do we prove this? Sorry, so I have to say this, right? Sorry, this is misleading. This is one step because that's the hypothesis. But here I don't need one step, right? I only need some steps because here, right, it's talk about, the structure of the transition matrix, right? Here I just need to be able to return to state I starting at J. I don't need to be able to do it in one step, right? but it still makes it into one communicating class. How so? The reason is something along the line of what we just did before, right? There's no Markov property. So to go from I to I, right? You can do a one-step conditioning to say you have to go from I to J and then go from J to I, right? Okay, so far. I might have to modify this, but so okay. What I'm saying is like if you want to return from I to I, right? You have to go from I to J, and then from J go back to I, right? But this, I think I'm doing something wrong here in the direction because this will be basically bigger than Pij P to the JIT for some T. So, okay. So let me say the idea and then I'll try to correct this, right? What we're saying is that here's I, right? You will go to J at the first step. That's with a positive probability with Pij. Now, if you, once you're there and you never return, meaning there's always zero, then you have a positive chance, right, of never return to I. So I think it's more like this, right? 1 minus Fi, the chance of never return to state I, will be bigger than Pij times 1 minus Fji, right? The possibility of never return to state I starting at I will be bigger than, right, the probability. Well, one of those possibilities is to go from I to J and never return, okay, from J to I. Is that clear? But, right, this is zero because state I is recurrent. But Pij, right? So this is zero because I is recurrent. And Pij is positive. That means that this guy must be zero. Or you are guaranteed to be able to go from J to I. But if you're guaranteed to go from J to I, that means that you must be able to do it in some step. That's the argument. Any question? All right. If not, then I think this is enough for today. Okay. We'll continue on Wednesday.